Hello everyone. Today we're going to talk about Gaussian discriminant analysis. The goal is to describe Gaussian mixture models, explain how to use them for classification, and show you a real-world data example focused on the automatic diagnosis of Alzheimer's disease. The prerequisites for this material are Gaussian random vectors and also the joint distribution of discrete and continuous random variables. However, in order to make the video as self-contained as possible, we're going to start by reviewing some basic concepts that we will need mainly about Gaussian random vectors. Okay, so what is a Gaussian? We'll start with Gaussian random variables. What's a Gaussian random variable? It's a random variable that has a density with this shape. This is a bell shape that is centered at mu, which is a parameter that we need to determine from data. And how spread out this bell shape is determined by a parameter sigma. So let's take a look at some examples. Here, mu is 3, so the density is centered at 3, and how spread out it is determined by the parameter sigma, which in this case is equal to 1. Sigma is the standard deviation, so it's the typical deviation of a point from the center, which is mu, and mu is the mean parameter. Here, the mean is -2 and the standard deviation is 2, so the density is more spread out and it's centered at -2. Here, it's centered at 0 and it's even more spread out because the standard deviation is 4. All right, so how do we fit these parameters, the mean and standard deviation parameters, when we have some data? So here I'm showing you a histogram, a normalized histogram of heights in a population. And we would like to fit the Gaussian so that it adapts well to the histogram, because the histogram is a non-parametric estimator of the density of it. Where do we have more people that have a certain height. We would like to adapt the Gaussian to that density, so we have a Gaussian model for the height of the people in the population. Okay, so this is not a great fit. Sorry, that was a terrible arrow. This Gaussian does not provide a great fit. This one either. How do we find a Gaussian curve that is well adapted to the data that we observe? Well, we do this using maximum likelihood. Here, the idea is that we can write down what the density, the joint density of all the data points is with respect to the parameters. So here I've already jumped in to write the log likelihood, but if we look at the density of all the data, so just to be very clear, we're going to model the data as IID random variables, and they are observed at certain points. Okay, so in the height example, these are the actual heights that we observe. Okay, and this is given by a Gaussian density if we assume that the data are indeed generated as samples of this Gaussian distribution. And if the data are independent, then this is going to factor into the product from 1 to n of the Gaussian density at each point. And here we're going to assume that this Gaussian density at each point has the exact same parameters, mu and sigma. If we take a logarithm of this, we obtain the log likelihood. And what we do is we want to maximize the log likelihood with respect to the parameters. We want to get parameters, we want to choose the parameters so that the density at the observed data is as high as possible. Okay, this is just a really quick review of maximum likelihood estimation. I encourage you to review it, for example, with the video on maximum likelihood estimation or using any other resource. But anyways, let's go on. The way we do this is by maximizing the log likelihood. Here we have to plug in the density as a function of the mean parameter and the standard deviation parameter. And if we do that, we get this expression. If we maximize this expression with respect to mu, what we get is, you can check, take derivatives, set the first derivative to 0 with respect to mu. What you're going to get is that the maximum likelihood estimator for mu is equal to the sample mean, which makes a lot of sense because mu is at the center of the distribution. For this particular bell shape, it turns out that the center of the distribution is actually at the mean. So then you use the sample mean to estimate the parameter. Okay, and this maximizes the log likelihood. By a similar argument, again, you take derivatives and so on. The best estimate for the standard deviation, here I've written it as the variance, which is just the square of the standard deviation, is going to be actually the sample variance. So there's a small detail here. Sometimes we write the sample variance with an n-1 there so that it's unbiased, so it's not exactly the same, but it doesn't really matter in practice. Okay, the maximum likelihood estimator for the variance parameter looks like this. Okay, it's an average of the squared deviations of the points from the sample mean. Okay, so we do this, and we obtain a very nice fit to the data. Okay. All right, so we're also going to be interested in Gaussian random vectors. What I showed you now is just a Gaussian random variable because it only has one dimension. Okay. If you want, we're modeling distribution of one feature. But normally, when we're doing machine learning, statistics, and so on, we have several features that we want to model jointly. And Gaussian random vectors are actually a very popular model to model. That wasn't, I wasn't at my best in the phrasing of that, but Gaussian random vectors are a very popular model for multiple continuous quantities. The idea is that you have a generalization of the Gaussian density that looks like this, and now it's parameterized by a mean vector, which is still the center of the distribution, except that now it's not the center of the distribution in 1D, it's the center of the distribution in D dimensions, however many dimensions the random vector has. And instead of a variance parameter, we have a covariance matrix parameter, which captures the variance in different directions of space. Okay, so here I do recommend that you go to the video on Gaussian random vectors if you want to brush up on this. But let me show you at least how the density looks like in 2D. And something very important about, so just to be clear, this is one dimension, this is the other dimension, and this tells you basically the density that we observe at each 2D point, and the mean is going to be there. Okay, the peak underneath, that's going to be the mean of the distribution. And the covariance matrix is going to determine how spread out these densities in different directions. If you look at the contour lines of Gaussian densities, they happen to be ellipsoids, and the shape of this ellipsoid is determined by the covariance matrix. Okay, if you look at what are these lambda and u's? Well, the axis of the ellipsoids are the eigenvectors of the covariance matrix, and how spread out the ellipsoid is along each of its axes is determined by the eigenvalues of the covariance matrix. Again, this is not super important for this video. I recommend that you go and review if you don't remember these things. All right, but I guess the take home here is the density of a Gaussian random vector is going to be ellipsoids in D dimensions, centered at the mean. How do we find the parameters of a Gaussian random vector? Exactly the same as in the 1D case, we maximize the log likelihood. Okay, so here I've spared you the calculations, but basically you write out the log likelihood under IID assumptions, and you find out that the mean vector is just going to be equal to the arithmetic average of all the points. Again, it's the center of the distribution, so this makes sense. In order to find the covariance matrix, this is actually the sample covariance matrix. Again, sometimes we would write an n-1 there if we want to make it unbiased. It's not a big deal. All right? So that's how we estimate the parameters. Here's an example of a data set where we have the height and the weight of a population. This is what the contour lines look like if we just use kernel density estimation, so a non-parametric estimator of the density to plot them. And this is what the maximum likelihood Gaussian model looks like. Okay, so it's not perfect because, this is not perfectly ellipsoidal. Clearly there is some kind of, it has a little bit of a banana shape, maybe. You squint your eyes, I think so at least. But, the ellipsoid is a pretty good model. Okay, so now we're going to talk about Gaussian mixture models. In order to motivate this, we're going to look at a different data set from the one I just showed you, which has data from about 4,000 men and 2,000 women from the US Army. And now we're going to fit a Gaussian to their heights. And what we realize is that the fit is not great. Okay, if you see there, the fit is not great, here either. Okay, like the best Gaussian does not fit the data that well, which indicates that the underlying data are not Gaussian distributed. I mean, nothing is completely Gaussian distributed, but the Gaussian is just not a great approximation, so we're going to try to come up with a better approximation. And you might remember that I showed you another data set, which is this one, where you actually got a really good fit using a Gaussian model. That data set only had the men in this population. Okay, so for the men, the Gaussian model is actually really good. So what does this suggest? This suggests maybe fitting a Gaussian to the men and then a Gaussian to the women and then combining this, right? And that's essentially a Gaussian mixture model. End of story. But let's look at the math. So what we're going to do is we're going to say, okay, height is this continuous random variable h, and it depends on the sex of the person. So we think that is an important factor that is going to determine the distribution of height. So what do? We model it. We incorporate it into our model as a discrete random variable s. And now what we're going to assume based on this preliminary analysis is that the conditional distribution of h of the height given sex is Gaussian. Okay, so that's basically the idea. In order to do, to model all of this, we're going to need the distribution of S. But S is just a discrete random variable that can be men or woman, man or male or female. Let's put it like that, male or female. So how are we going to compute this distribution? Okay, take a moment to think about it. Well, what are we going to do? We're going to say, okay, the probability of being a woman or being female is going to be this number plus this, divided by this plus this. Okay, this wasn't a great explanation. It's just a fraction of women in the population. Okay, that's better. Okay, and this is a fraction. There's more men than women. These are estimates for the probability mass function, the PMF of S, which is a discrete random variable. Okay, what about the conditional distribution of H given that S is female? How are we going to fit this? Let's just reason by common sense. What we're going to do, we're going to take all the women in the population and we're going to fit a Gaussian to them using maximum likelihood. Okay, we're going to take the average height of the women in the population, that's going to be the mean of the Gaussian. We're going to take the sample standard deviation of the height of the women in the population, that's going to be a parameter sigma. And if we do that, we get a pretty decent fit. Same thing for the men. I actually already showed it to you to motivate this whole thing. Boom. Okay? Pretty good fit. Great. So now we actually want to have a model for the whole height, for the general height in the population without S. So how can we achieve this? We want the marginal PDF of H. And if you remember, and if not, go review the joint distribution between continuous and discrete random variables. If you remember, if you have the conditional PDFs of a continuous random variable given a discrete random variable, you can actually obtain the marginal by just summing them all up as long as you weight them by the PMF, the probability mass function of the discrete random variable. Okay? And if we do that, this is what we get. Of course, these guys are Gaussians, so we get two Gaussians that are weighted by the probabilities. Okay, the probability of being female times the corresponding Gaussian plus the probability of being male times the corresponding Gaussian. And let's just plot this PDF and see how it fits the data, and it fits the data very, very well. Okay, much better than the Gaussian model. Here, you can actually see this formula a little bit more intuitively. We have the women and the men. These are the women here, and these are the men here. What we do is we weight the conditional distribution, which is Gaussian, the conditional density, which is Gaussian, by the corresponding probability, and then we add them all together. And this gives us this shape, which produces a very decent fit to the population. Okay, so that's basically a Gaussian mixture model. If you were in more than one dimension, you would do exactly the same, except that the conditional Gaussians would be multidimensional. Okay, but otherwise, same idea for Gaussian random vectors. Okay, so now we're going to think about how we would use this model to perform classification. So what is classification? Imagine that you get the height of a new person, and you want to guess whether they're male or female. How are you going to do it? Using our model. Well, using our model, essentially what you want is the probability, the conditional probability of sex of for example, female, given that particular height. Okay. So I'm going to just write it down. So imagine that the height is h. What you want is the probability, so the PMF of S given the height of, let's say, female given h. Okay, this is what we want to compute. We don't have this, but we can derive it, as we will see in a moment. But remember that what we have is the PMF of S, the conditional densities of H, the continuous random variable, given S, given sex, and we use that to compute the density of height. We have just basically one piece missing, which is the conditional probability of sex given height. In order to get it, what we do is we apply the chain rule for continuous and discrete random variables. Again, if you don't remember this, please go and review it. But it turns out that for discrete and continuous random variables that are jointly distributed, multiplying the PMF by the conditional PDF is exactly the same as multiplying the PDF by the conditional PMF. Okay? So if we want to find, let me maybe highlight this a bit. If we want to find this guy, because in our case the discrete random variable is sex and we want sex given height, then what do we need to do? We just divide this by that. Okay? In order to remind you a little bit what this actually means, it's always good to try to think, when you have an equation, try to think, what is this object? This object is a little bit like the joint density of the discrete and continuous random variable, except that they don't have a density because they're not continuous, or the joint PMF if they were discrete, because remember that by the chain rule, the joint PMF is just equal to the marginal PMF times the conditional, and the same for the PDF. The joint PDF is equal to the marginal PDF times the conditional. In this case, we have a marginal PMF times a conditional PDF, or vice versa on the other side, because the random variables are discrete and continuous. But we can actually visualize this, and it would look like this. In the case of the heights, we have the conditionals weighted by the probabilities, or looked the other way, you have this is what I mean, the marginal density multiplying all the possible conditional PMFs. Okay, and what we want to do is we want to say, okay, we observe, I don't know, for example, that the height is 160, so we will go here and we will say, maybe these are the 2 points. I'm making it up, right? My 3D, I'm not really good at like visualizing things in 3D, but let's say that those are the 2 points. We're gonna see what is essentially the fraction between them, right? We're gonna divide by this to see how much higher, for example, this point is than this point, or vice versa. Okay, this is what we're doing when we're applying the chain rule to compute this from these quantities. Okay, so hopefully that was a bit helpful. And again, this is not really a density because this is just lying on a single line. So it's not a 2D density, okay? That goes up like a surface in 3D, okay? It's just 2 lines because this random variable is discrete. Okay, so how do we compute probability of female given that the height is h? Here I'm calling female 1, just arbitrarily. Well, we apply the chain rule. We have the marginal times the conditional divided by the marginal PDF. The marginal PDF, we already saw that we can compute it by this weighted sum of the conditional PDFs. And this is how it looks like. It's a bit of a messy expression, I'm not going to lie to you. But basically what did we do? We just plugged the conditional Gaussians everywhere and weighted them by the corresponding discrete PMFs. So it's not that scary. If we plot this thing, it actually, this is the expression. Okay, once we simplify everything, I'm not going to do it now, but you can go ahead and try it on your own. Once you simplify everything, you get an expression that is kind of similar to a logistic. For those of you that have seen logistic functions, it's kind of similar, but it has this square term, so it's not really a logistic. Okay, and the reason is because the two conditional Gaussians have different variances. But that's a little bit of a technical detail. The point is that when I plot this, here the black line is probability of male. I should have written maybe male more than man, I don't know. Given height, and the dashed line is probability of woman or female given height, and it makes a lot of sense, right? So there's a certain cutoff here at 160 whatever, and here the probability of female is really high, here the probability of male is really high, which makes a lot of sense because in the population, most people that have these heights are female, most people that have these heights are male, and here we don't know, right? There's, half-half, let's say. Okay, this is essentially what this conditional PMF is capturing. Okay, so now we're going to apply exactly this idea where we model our data using a Gaussian mixture model, and then we derive the conditional PMF of the discrete random variable in order to do classification in a medical application, in particular in diagnosis of Alzheimer's disease. So for those of you that don't know, Alzheimer's disease is a terrible neurodegenerative disease that causes, I think it's around 60-70%. I looked this up in Wikipedia. I am no doctor. I'm not claiming a lot of expertise here. It causes 60-70% of cases of dementia, and it's really a terrible problem. It's not very well understood. So there's a lot of hope that maybe applying machine learning techniques can help to diagnose it earlier, so that studies can be populated and patients can be treated, but it's really a not very well understood disease, unfortunately. Okay, so typically it's diagnosed via positron emission tomography, PET, but that is invasive and very costly. And it would be quite interesting to be able to do a quick diagnosis just using MRI, okay, because it's non-invasive, and it's less costly, although MRI is still pretty costly. Okay, this is of course a very idealized application in the sense that we're just going to look at a very specific example of how you would go about doing this. You could apply, in principle, any machine learning algorithm to this, and in particular, you can apply deep learning neural networks to the whole MRI. But today, we're going to do it in a bit of a different way. The goal is to diagnose Alzheimer's using MRI scans. Okay, so what does an MRI scan look like? This is how an MRI scan looks like. It's in 3D. I'm going to draw your attention to this part of the brain here, which I think is here and here. That's the hippocampus. This part unfortunately shrinks when you have Alzheimer's. So this is the brain of a cognitively normal patient, a patient that does not have Alzheimer's. Patients that have Alzheimer's, some parts of the brain actually shrink. And this causes problems because the hippocampus and other areas of the brain are what you use to remember things and to learn stuff and so on. And when these areas shrink due to Alzheimer's or due to some other reason, learning and memory are affected, unfortunately. Okay, so how are we going to try to diagnose Alzheimer's disease? We're going to look at the volume of the hippocampus, which can be obtained by segmenting the MRI. Okay, you process the MRI, you find the hippocampus, you see how big it is. An important part is that then you divide by the whole volume of the head of the person. The idea here is that people whose hippocampus have shrunk are going to have smaller hippocampi, I guess maybe that's the plural of hippocampus. But we like only relative to their head. So I have a huge head, my hippocampus will probably be quite big even when it shrinks if I get Alzheimer's. Hopefully I won't. So we have divided by the whole head volume. And here we're showing the volume of the hippocampus and of another part of the brain called the entorhinal cortex, which is also related to dementia and Alzheimer's. Okay, and what we see here, the black points are patients with Alzheimer's. The light gray points are patients that do not have Alzheimer's. We see that patients with Alzheimer's tend to have smaller hippocampi relative to their brain volume. And the patients that do not have Alzheimer's have larger hippocampi and larger entorhinal cortices. I don't know what the plural of cortex is, to be honest. There is a lot of overlap though, okay? So there's a lot, like you can't really see it very well, but a lot of gray points are also there. So it's from these two features, actually, it's not completely obvious how to do this classification. And as I said, I'm just showing you a very specific example of how to do this. You would probably want to use more volumes, and you could even use a neural network to not have to extract the features yourself and just put the MRI into a neural network. The problem with that is that then your estimate might not be as interpretable. You won't be able to tell a doctor, I think this person has Alzheimer's because the hippocampus has shrunk or because the entorhinal cortex has shrunk. Okay. Anyways, I don't want to get carried away. I'm really interested in applying neural networks to this kind of stuff, but that's not our topic today. Today we're going to see how to do it with Gaussian discriminant analysis. All right, so that's the problem. Okay, we have this data. We have this data set where we know the volumes of these two areas of the brain for a bunch of people that have Alzheimer's and do not have Alzheimer's. And we want to have a model that tells us the probability that someone that comes in has Alzheimer's or not. Okay, that is able to classify, to diagnose Alzheimer's automatically from an MRI that measures the volume of the hippocampus and of the entorhinal cortex. I'm probably also mispronouncing entorhinal. Sorry, I do what I can. Okay, so the classification problem in general is that we have pairs, we observe pairs of feature vectors xi. In our case, xi is two-dimensional. It has these two volumes. And the class label yi. In our case, the labels are either cognitively normal, so no Alzheimer's, or Alzheimer's. And our goal is to classify a new data point, x, which is going to have dimension 2. It's going to be two new volumes. We're going to have to say, oh, this person we think has Alzheimer's or not. Okay, so we're going to do this using a probabilistic model where a certain random vector x is going to represent the features, in our case, two-dimensional features, and y is going to represent the class, in our case, the diagnosis, Alzheimer's, no Alzheimer's. Okay, so how do we classify x if we know, and this is a very big if we know the joint distribution of x and y? Well, what are we going to do? We're going to compute the probability that y has a certain value conditioned on having observed those particular features. Okay, again, this is a very big if because in general, we are going to have to estimate this joint distribution from data, and this is the whole key to statistics and machine learning. Learning distributions is actually very challenging, mainly because usually we have a lot of features and we have the curse of dimensionality. In this particular case, so that I could show you things in a simple way, we only have two features. So the curse of dimensionality doesn't really play a role, but I just wanted to mention here that I'm saying estimating the joint distribution in a very cavalier way. Usually we have to make some simplifying choices in order to even be able to approximate some kind of distribution, and that's a key issue in machine learning. But again, let me not get derailed. Let's move on. So in Gaussian discriminant analysis, what we're going to do is we're going to model the features using a Gaussian mixture model that incorporates the class as a discrete random variable. That's the idea. Okay, so we're going to, oops, this should be an F, right? Yes, this should be an F. I mean, a bit of a stickler for this kind of stuff. Remember, the features have densities. So we're going to, for each of the classes, in this case, no Alzheimer or Alzheimer, but we could have more classes, we're going to fit a Gaussian to the training examples that had that particular label, like we did for the men and women, right? Okay, and now I have to suffer. I should do this at the end. Okay, and what are we going to do for the marginal PMF of the class? As with the men and women, we're just going to look at the fraction of data points that are in each class. Okay, just the fraction of data points, fraction of people that have Alzheimer's, fraction of people that have no Alzheimer's. Okay, I'm going to fix the density again here. Remember, this is a density of the features conditioned on the class. Again, and then afterwards, what are we going to do? We're going to classify the test data based on the probability, the conditional probability given the features that we actually observe. Okay, and we need to estimate this guy from this. But we've actually already shown you how to do it for height and sex. It's exactly the same idea. Okay, it's actually quite simple. Okay, so our training data. Remember, black points, Alzheimer's, light gray points, no Alzheimer's. We fit a Gaussian. And here we're actually going to see about this overlap that I was talking about, because here you can't really see it very well that there's overlap there. There is quite a bit of overlap. You see it in the Gaussians that have been fit to the data. Okay, these are the contour lines of the density of the Gaussian fit using only people with Alzheimer's. These are the contours of the density of the Gaussian fit using people that do not have Alzheimer's. And you can see that there is an overlap. Okay, but those are our conditional distributions. Again, I wrote a P here. So I'm going to change it for an F, and I'm going to apologize. Okay, I don't know. Like, I try to avoid typos, but it's, yeah. They're the bane of my existence. Anyways, so now the way we're going to do classification is we're going to look at the probability of a class given the features, the probability of each class, Alzheimer's, no Alzheimer's, given the features that we observe, given this two-dimensional vector with volumes. Okay, and what are we going to apply? The chain rule. Okay, we're going to apply the chain rule of discrete and continuous random variables here in the denominator. Why did I put, like, I don't know what got into me. Okay, this is just f of x. Okay, we compute f of x again, taking all the conditional PDFs, multiplying by the corresponding probability and adding them. This is exactly what we did with height. I'm just going to go ahead and change the P to an F again because I'm a bit OCD. Anyways, so now again, we put in the conditionals, which are Gaussians. Okay, and the parameters, again, it's important to remember the parameters of the Gaussians, which is this mu y and this covariance matrices. And in this case, the covariance matrix K, mu K. These are the parameters that we have estimated using only these subsets of data. So mu1 only with the training data corresponding to class 1 and sigma 1. Mu2 and sigma 2 using only the training data points with class labeled class 2, and so on and so forth. Okay. Now we put it all together like this to get the probability of each class given the observed data. And when we do that, this is how these probabilities look like. Here, I'm plotting the probability of Alzheimer's according to the model. And so just to be clear, along this line, the probability is 0.75, along this line is 0.5, along this line is 0.25, 0.1, and so on. So the model thinks that the people inside here, okay, are more likely to have Alzheimer's than not. Okay, this is how the model classifies. And, you know, given the data, it looks pretty reasonable. So we're going to diagnose Alzheimer's if this probability is larger than 0.5. You could modify this threshold depending on whether you care more or less about true positives, false positives, and so on. We're not going to get into that, but that's actually an important issue if you're looking at classification. But it's a little bit beyond the scope of this video. Suffice it to say that you might want to choose this threshold depending on how much you care about being wrong in one way or the other. Okay, but for now, we're going to just diagnose Alzheimer's if the probability is larger than 0.5. The error rate is 24%, so we're wrong in 44% of the training data. we need to compare this to a very naive estimate where we might say, because there's more people that do not have Alzheimer's, what we could say is, oh, no one has Alzheimer's. Okay, this is a very dumb classifier, but it does, like its error rate is 27%. So by looking at these two volumes, we can bring down the error from 27% to 24%. Not amazing, but we're only using two volumes. And if you look at the data, they're quite on top of each other. We'll go back to this issue a little bit later, evaluating our results, which is always important. But for now, the error that we achieve is 24%. However, is this what we really want? Like, would we be very happy if the error rate was 0 here? What do you think? We would not, right? Because these are training data. And if I used like a very fancy neural network and, tweaked it, I would probably achieve an error of 0%, but I would probably not be able to generalize to new data, right? So there could be overfitting. We need to look at the performance of our algorithm on test data, on held out data that is different from the one that we used to train. Okay, this is, I can't overstate how important this is in machine learning. So this is our training set, the Alzheimer's Disease Neuroimaging Initiative training set. We're going to use a completely different training set from patients that are from a completely different cohort. Cohort just means the group of patients that are considered. And this other group of patients from the National Alzheimer's Coordination Center. And these patients were selected in a very different way. And the first study is more controlled. This second study is more in the wild with data from several hospitals. So the characteristics of the patients are probably very, very different. And you can actually see it, right? Like if you look at just focus on the distribution of the volumes, you can see here that there's more patients, for example, that have larger volumes. So maybe there's also a bit of a younger population. So we can test our algorithm there, and this is the ultimate test actually, when you take a completely different population and you test your algorithm that you have trained on this other population. And what we see, again, like our estimate of Alzheimer's here is people that are here. What we see is actually that the error is pretty reasonable. So again, we diagnose if the model tells us that the probability of Alzheimer's is above 0.5. Our error here is 18.5%. This looks amazing compared to the previous one, but in this population there's less people with Alzheimer's, so we should hold our horses. If we just said that no one has Alzheimer's, we would make an error. We would have like a fraction of errors of 21.6%. With our algorithm, we achieve 18.5%, okay, which is significantly better, but still not as spectacular as you might have thought. Okay, so you might have noticed that this decision boundary is curved in a bit of a weird way. So you might have wondered why do the decision boundaries look like this? They're actually quadratic lines, decision boundaries. We're going to see why in a moment. And Gaussian discriminant analysis, as I have just defined it, is often called quadratic discriminant analysis because the boundary lines are quadratic. Why are they quadratic? Because the reason they are quadratic is that this probability of the class given the features has this form that we derived. When we compare the probability of two classes, let's say A and B, and we see where they are the same, okay, that's the decision boundary. That's the definition of a decision boundary, right? If we, in the case of two classes, if we decide that 0.5 is the threshold, well, if we write this down, we basically divide this guy for like the value of this guy for A when y is equal to A by the value of this guy when y is equal to B. You can check that we obtain something like this. Okay, the denominators basically cancel out, and you're just dividing the numerators basically. You get something like this, and now you take logarithms. What happens is that you get a quadratic function of the features, and that's why the boundaries are quadratic. This quadratic discriminant analysis, And what this suggests is you might say, okay, but actually I might prefer a linear. Okay, so it's called quadratic discriminant analysis because these guys are quadratic curves. You might say, okay, I want a linear boundary because this is easier to explain to the doctors, for example. Or I think it's going to be more robust when I apply to a different population because I don't trust like these things, you know, like I don't think the boundary should actually be quadratic. Okay? So how could you achieve a linear decision boundary? Well, we derived this equation for the decision boundary, and what you have to realize is that if you expand this out, okay, if you expand this out carefully, what you end up with is that the quadratic part looks like this, and then there's this minus, and then there's this other quadratic part here. And if you set the two covariance matrices to be the same, then these guys just cancel out. Okay, I know that I'm going a little bit quick through this, but you just need to compute this out on your own and convince yourself, just giving you kind of an intuitive idea where this comes from. If you set these two covariance matrices to be the same, then this will cancel out and you will get a linear boundary. How can you do that? Well, you have to go back to think about how you have fit the model. The way we have fit the model is we have taken the Alzheimer's people. Okay, we have taken the Alzheimer's people and we have fit the mean and the covariance matrix of their density using only that subset, the subset of people with Alzheimer's, and we've done the same with the people without Alzheimer's. But we can actually force the two covariance matrices to be exactly the same in the following way. We can say, okay, let's estimate the mean of the Alzheimer's people and the mean of the people without Alzheimer's. Okay, these two means are going to be separate. These are the parameters of the respective distributions. And now let's center all the data using those means, using the mean of the Alzheimer's people for the Alzheimer's people and the mean of the non-Alzheimer's people for the non-Alzheimer's people. And now let's compute a single covariance matrix. And then, when I compute the probability of Alzheimer's given the features, I'm going to get linear boundaries. And that's exactly what you do if you do linear discriminant analysis. So here actually what you end up with a convention that is not that different, but I want you to look at this guy here. Like this part actually is quite different. Here, okay, I've done what I just said, and I forced the two covariance matrices to be the same, and I used all the data to estimate them by centering first. And this is what I get. Okay, these are the new conditionals. When I recompute the probability of Alzheimer's given using these new conditionals, instead of getting these quadratic curves, what I get are these linear boundaries, and this is called linear discriminant analysis. Let's check out how good it is. The training error rate is very similar to the quadratic one. Remember that the fraction of patients with Alzheimer's in the training, because we need a baseline, right, to compare to, is 27%. And on the test, it's exactly the same. Okay, so simplifying the algorithm makes no difference. So now let me ask you, how do you think we could improve this model? Okay, and this maybe is just a good opportunity to review how you evaluate the results of machine learning algorithms. So first of all, the first question you should ask yourself, do we have overfitting? Yes or no? We don't have overfitting because the training error rate and the test error rate is, the training error rate and the test error rate is actually, the test error rate is even better. Okay, that's just because the population is different, but basically you don't see that you have a very, very low training rate, a training error, and a high test error. Okay, so no overfitting. Do we have underfitting? This is a bit tricky. Do you think that we have underfitting? So if I go back to visualizing our data, which, and this is very important, you often cannot do in high dimensions. We're very lucky we only have 2 features. If I visualize my data, here you're not going to be able to do magic. And we see this also by the fact that the quadratic discriminant analysis, which tries to fit this boundary a bit better, it does not do better than the linear one. So no matter how you squirrel your way around this, it's just like the 2 features are not discriminative enough. Okay, they give you this discriminative power that we're achieving with the algorithm, you're not going to be able to do better. So there's no underfitting either. What you need to do to improve the results here is either gather more data, but above all, gather more features. Like we need more features so that we can actually distinguish between the patients. And again, one way of achieving that would be to just take the whole MRI and put it into a deep neural network. That brings about other challenges, such as interpreting the result and convincing the doctor that it's doing something reasonable. Okay, so what have we learned? We have learned what Gaussian mixture models are, how to use them to perform classification, and we have worked through an example to a real-world data set for automatic diagnosis of Alzheimer's disease. Thank you very much.